Hello, everyone. Welcome back. Happy Friday. The problem set for line coding is due today. The problem set for the OFDM unit is going to be due a week from today. So that's available now. And also today, I think we are going to wrap up spread spectrum, I hope. Before we launch into that, any questions from you? Okay, so let's switch over. And let's recall where we left off. So we are going to be looking at this lovely mess. And let me see if I can actually hide. Yeah, that'll work. So we are going to be trying to do a detection routine in which everything on the right-hand side of this diagram is being done at one location. So we're going to try and decode RK 1, 2, 3, 4, 5 up to M all at once. And the idea being is that at a base station, we're going to have all of these signals available to us, and we can use knowledge of one to help us either eliminate or to decide that a certain vector of symbols is more or less likely than another. That's in general termed the multi-user detection problem, or MUD. And if you adopt that line of reasoning, then we had some, oh, hey, they're back. We had some abbreviations for the different received symbols stacked in a vector R sub k. We're going to have a matrix full of autocorrelation values, and these are autocorrelations between spreading codes, so Ci and Cj. And on the diagonal then would be autocorrelations between Ci and Ci. And D is just a diagonal matrix of gains, so either channel gains and transmission gains. And then what we're going to be modifying, this whole matrix expression is going to be modifying the vector of sent symbols, which I'm calling the vector xsk. Sorry. Of course, each of those symbols is going to be corrupted by its own sample of the noise process. And so we've got a vector nk. And then something that we derived last time, but maybe I didn't call enough attention to it, was the statistics on this nk vector. So what we got last time was that the expectation of the nk vector with the nk vector conjugate transpose is going to be the power of the additive Gaussian noise process, the power spectral density, times the autocorrelation matrix, or sorry, the cross correlation matrix R sub k. Okay, so how do we get that? Well, I think if we scroll back to, nope. Yeah, this slide. So again, this is like the expectation of each element of nk with another element of nk. And so what we can do is we can, so this is like, so this value is going to be sitting in here, where this is the ith row and the jth column. And we can express that as n vector times n vector transpose, conjugate transpose. Because if n is tall, then n transpose is wide, and that means their product will be square. Okay. So the notation that I have on this slide now encapsulates that. So I'm taking the expectation of now a matrix, and every element of that matrix is can be given to us by the results from 3 slides ago. Okay. So let's, you know what I'm going to do? I'm going to clear up this slide for a moment. And actually, I'm just going to start over. blank. Good. Okay, so the idea here is that we would like to pick the vector of symbols that is most likely to be sent given the received information that we have. Okay, that's the essence of max a posteriori or map detection. And so what I'm saying is pick the SK that maximizes this probability. Call that SK hat. That's our best guess at SK vector. And then we're going to use Bayes' rule. So we're using Bayes to go and rewrite that conditional probability. And then we say that because we're maximizing or we're optimizing over the S vector, this has no dependence on S vector. So maximizing with it in, with it out doesn't matter. And then lastly, the last simplification you can make is that if this is constant, i.e. if we have equal priors, then multiplying everything in a set by a constant doesn't actually change the order which is biggest. So if you have a constant or all the priors are equally likely, then you get what's called max likelihood optimization. And we are simply left with trying to maximize this function, the probability of receiving data RK given SK was sent. And again, we're going to consider all possible SKs, right? So in general, we'll have a bunch of numbers at the end of the day, and we're going to pick the SK that gives us the biggest number. Okay, so, and the last thing I wrote was just expanding our expression for RK, the vector RK, in terms of this matrix expression that we have at the top of the slide. Okay, so if we are conditioning on SK, so now I can go to the next slide, and now I have enough time that I can do it out nicely. So let's talk about the probability that of receiving RK given SK was sent. And again, we have the expression for our vector K as our matrix K times the diagonal matrix times the vector of symbols plus the noise vector given the vector of symbols. And so the claim is that this is all deterministic. And this is actually the only random thing. And so now it's we've got to figure out what is the distribution of this random variable, or random vector, I should say. And it's going to be Gaussian vector, because we're assuming that the noise is additive, white, and Gaussian. Which means if I pass that through an LTI filter, that the result will be Gaussian. And then I'm going to shift it. So this represents a shift or an offset to the noise vector n sub k. Okay, so this is then going to be nk is going to, sorry, not total vector, is going to be normal with a mean of RK, I think. Yeah. So this is the mean. And the variance is going to be RK. So that means that this probability is the same as, well, we're just going to use the joint Gaussian distribution here. So 1 over pi times the noise density to the negative m, remember capital M is the dimension of our vectors, times the determinant of the chipping code covariance matrix, or cross-correlation matrix, times the exponential of -1 over script n times the point in the M space shifted by the mean and conjugate transpose. So that'll be, it's a column, now it'll be a row, times the covariance matrix inverse times the same vector again, but now with no transpose. Okay, so this is simply the joint distribution function of this noise vector nk that has been shifted by the mean value that we have up there. So you're wondering, where did we get the covariance matrix from? Where did this come from? Well, remember that we just said that the expectation of nk, the outer product, if you like, of nk with nk is n over 2 rk. And so all I've done is I've separated out the n, and it goes over there, and then the rk goes here. So this is now our covariance matrix for the noise process. All right, questions on that? This would have been really hard to do in the last closing minutes of last class, but I realize that I'm bridging classes, so. Anyone need help remembering where we came from or thinking about where we're going? Okay, so remember that this whole time we're trying to maximize this expression over all possible vectors sk, which means if there are ever anything in here that don't depend on sk, then we actually don't need to consider them, including this entire scaling factor, and I think this scaling factor as well. These are not dependent on sk. So while they will change the probability, they don't change the relative probabilities of each of the possible SKs. Okay, so again, in my notation, our best guess for the symbol vector is going to be now the arg min over possible SKs. This changed from a max to a min because of this negative sign of rk minus the matrix r times d times s conjugate transpose times rk inverse times that same vector. Which, if you want a more compact way to write this, well, actually, here's a check of your understanding. What is the dimension of this quantity? Matrix, vector, scalar, none of the above?
Scalar?
Yeah, exactly. So it's like an inner product, except for this thing is kind of skewing our inner product, right? So one way to write this is if I could split RK inverse into two halves and put one half on the left and one half on the right, then I could actually write this as the inner product of a vector with itself, which is just the norm of that vector. And so a fun fact is that RK is what's called a positive semi-definite matrix. Just because it's structure, we're looking at the covariance, the cross correlations of all our chipping codes, which means on the diagonal we have a autocorrelation, so those are all going to be non-zero. And one property one of many properties of positive semi-definite matrices is that they have square roots. Is that RK can be written as RK, a new matrix, RK to the 1/2 times that same matrix itself. So that we call it the matrix square root. This is not, let me point out, this is not the square root of all the elements of RK. That's not how it works. But there is a matrix, I don't know if you don't like that notation, there is a matrix called A that if I multiply it by itself, then I get RK. And so just the common nomenclature is A is the matrix square root of RK. Okay, and it gets this notation. But I do want to remind you that this is not the same as the square root of every element of R. Okay. And another fun fact is that if a matrix is positive semi-definite, then its inverse is also positive semi-definite. And so I'm going to use the same result not on RK, but on RK inverse. So then this is the same thing as the minimization of this vector. So RK to the negative 1/2 times RK minus RK d SK. Okay. So I've done the thing that I promised. I've split the capital RK inverse into 2 halves, and therefore what we have in the above line is an inner product, a vector with itself, and that's the same thing as the size of that vector squared, the norm of the vector squared. Okay, and that's, I think, as far as I can reduce this. I have boiled this down as far as I can. So what are we left with? That's the big question. Well, first off, we're at the base station. Remember that this whole operation was predicated on being at the base station and getting data in. That data looks like the vector RK. So this is data coming in. Capital RK, this is a property of the chipping codes of C1, C2, C3, etc. And the same with this RK. So these are, once you know the chipping codes, then you know capital R. And again, we're sitting at the base station, and so you can think of we are Verizon, and we have assigned all of these phones to have their specific chipping codes, and so that's something that we know. We can use it to our advantage. The D matrix, remember that was the matrix of powers and channel gains. So this is typically something, the powers you can actually communicate, like, hey, user 1 is transmitting at -5 dBms or whatever. But the channel gains you're going to have to estimate. So in general, we're going to need to estimate this. And then the only thing that's left is the SK. And so the SK is actually the thing we're trying to optimize over. You can think of it as the independent variable. This is like the X in your calculus 1 problem. We're trying to optimize over X and find the biggest function value over the span of X, except now our X is a vector. But that vector is drawn from a finite set, right? It's not a continuous thing. The vector SK, right? It's going to be some quam for user 1. It's going to be some quam thing for user 2, for example. It's going to be some quam thing for user M. And so, actually, this is a moderately challenging critical thinking exercise. How many possible SKs are there? If we're using quam and we've got M users, what's the set that we're trying to optimize over? What's the size of it anyway? Let me help you visualize this in a slightly
Is it
less
4 times m?
close. Close. So user 1 is going to have one of those constellation points. User 2, one of those constellation points. All of them, one have 4 constellation points, and the 4 is from Quam. So it's going to be, the size is going to be 4, not times m, but raised to the m. Right? User 1 can have 4 options. User 2 can have 4 options. User 3 can have 4 options. So we're doing 4 times 4 times 4 up to the total number of users. So this is the size of, sorry, it's the possible SK vectors. That's going to be it. I'll say it. It's the total possible values of SK can take. And so what that means is, unless you have other kind of optimization things working in your favor, that in order to do this operation, this minimization, at the base station, you'll need to work out this function once for every possible set of SKs that you can have. Okay, so that means we need to run this 4 to the m times during every symbol period. Now, okay, if m is, I don't know, 2 or 3 or 4, this is not such a big deal. We're going to do a bunch of matrix math. Computers are good at matrix math. We'll only have, I don't know, a dozen or 2 dozen options to decide between. No big deal. But as the number of users in the cell grows, like 4 to the 200 is an immense proposition, even for a computer, especially if you want to do this quickly. All right, so if I have 200 users all using the same base station, this becomes really hard to do quickly. Not impossible. If you had all day, you could do it. But the fact that you have to do it within each symbol period and then start over means it's very easy to get behind. Okay, so that actually motivates what comes next, which are going to be suboptimal alternatives. But I want everyone to be okay with the fact that if you had all day, you would do this and you would get the best guess, the optimal, the maximum a posteriori guess about what was sent from every user. So I'll pause here for questions on that. Okay, and this is the pictorial interpretation of what we just derived, is that at the base station, you're going to have to do this operation over all possible SKs. Yeah, sorry for the angle, but I couldn't get it to fit otherwise. I can see little videos of you going. But then once you've done that at the base station, then you can put out your optimal guesses, S hat 1, S hat 2, S hat 3. And here, if you're doing 16 quam, then it would be 16 to the m. But I think we started this assumption that everyone's using equal energy symbols, and so that's why I used 4 quam on the last slide. The same idea holds if you do 16 quam. It's just it gets out of hand even quicker. Okay, so the frowny face means we're going to look for suboptimal alternatives. Right. If I can't do the optimal thing in the time that I'm given, then maybe I can do something suboptimal. I think you have all employed this strategy with homework, probably in this class, probably even today. Too soon? Okay. So let's look at some suboptimal alternatives. Oh, sorry. This was I did this out of order, or 2 slides ago. So one alternative is what's called a decorrelator. And you have the same setup. Again, we're sitting at the base station. And instead of doing this whole big operation where we're looking over all possible symbols that were sent, let's just do a very quick matrix multiplication. And the matrix is RK times D inverse. So let's derive why this would make sense and maybe how far away from optimal it actually is. I didn't give myself anywhere to work on this. So let's insert a slide here. Okay, so this is going to be the decorrelator derivation. Okay, so we're going to start with the received data vector. And remember, we're trying to tease out the symbols, right? We're trying to get at this thing. And so I think a reasonable thing to do would be to just try to like algebraically isolate it. So what would that mean? That would mean multiplying both sides by RK inverse. So let me use another color. So let's put RK inverse on the left, and then RK inverse on the right of the equal sign. And then maybe D inverse on the left, and then maybe D inverse on the right of the equal sign. And what does that leave us with? It leaves us with SK plus D inverse RK inverse NK equals D inverse RK inverse RK. And so the decorrelator is actually it's the derivation is not very involved. Is because what is this thing? I don't know. Let's forget about it. So the decorrelator says SK hat is simply this thing, and forget the noise. Right? It's saying that, hey, I can solve for SK as D inverse RK inverse times RK plus some other stuff. That other stuff depends on the noise. I don't know anything about the noise. If I assume it's zero mean, then maybe this is a reasonable thing to do. But this is just simply D inverse RK inverse times RK. And then basically do what's called a hard decision. Maybe you've seen this in the textbook. He uses this DEC operator quite a bit, and basically just that amounts to taking the sine, or maybe the sine of the real part and the sine of the imaginary part, and just saying, you know, wherever this vector happens to land, say it lands here, then just say that that maps to this constellation point. Okay. We're doing nothing intelligent about the noise or anything like that. We're just saying once you transform this vector with this matrix, it's going to land somewhere in the space, and then just pick the closest constellation point that you can. And do that for all M users. So I promised you suboptimal alternatives, and this is certainly one of them. But we should also take a peek and pause and establish how suboptimal these are, or when are they reasonable things to do and when are they not. So let's take this line and rewrite it as, well, RK D inverse RK. minus RKD inverse times the noise. And if you like, so I guess my question is, what happens if there is a small eigenvalue of Rk? So if, say, lambda min of Rk is small, then when I when I invert Rk, then I'm going to get a very large component in Rk inverse. I haven't introduced this notation, but lambda means an eigenvalue, and lambda min would be the smallest eigenvalue, and lambda max would be the largest eigenvalue. We can talk about large and small eigenvalues because the Rk matrix is Hermitian symmetric. Therefore, its eigenvalues will be real. So we don't have to talk about magnitudes. We can just talk about eigenvalues. So that means that if this is true, then all of a sudden, Rk inverse times Nk is going to be, in some senses, big. And I'm playing pretty fast and loose here. I'm just using big and small. But the idea is that it's going to be so big that it could wash out this thing. It could wash out the thing that we're actually going to be making our decision on. Which would mean basically we are going to be just deciding at random, because the noise will actually dominate the actual data that we're going to get, the signal that we're actually going to get. So the decorrelator technique would work if we were guaranteed none of our covariance matrix and eigenvalues were small. And this is going to be true if the autocorrelation of everyone's chipping sequence is very impulse-like. So this, the lambda of Rk, say lambda I, is going to be approximately the autocorrelation of Ci with Ci. Okay, so this is the idea that your chipping sequence ought to have a nice strong peak at 0. But if anyone's chipping sequence is, out of sync, then this peak is going to diminish. And so we're going to get a smallest eigenvalue. So this can happen if your chipping sequence is out of sync. The other thing that can happen, like we've just been talking about the R matrix, but the D matrix also plays a role here. And in particular, if any of the channel gains go to 0 or approach 0, then all of this whole argument also applies to the D matrix. And remember, the D was comprised of the channel gains times the transmit powers. And so if any of these channel gains become small, then the exact same argument applies. Is when I invert a small thing, I get a big thing, and so we end up amplifying the noise more than we'd like. But I mean, let me not sell it short here. If you can guarantee everyone is in sync, and you can guarantee everyone's channel gains are not going to go to 0, the decorrelator is a super fast way to get a best guess, or to get a guess, a reasonably good guess as to what was sent. Okay, there's no optimization, there's no search. Right, all this involves is two matrix inversions, one of which is diagonal, so it's just flipping a bunch of numbers, and then a matrix multiplication. So this can be done very quickly, is my point. And the complexity, or the algorithmic complexity, does not bite you like it did in the maximum a posteriori optimal decision making. Right, the matrices get bigger as m gets bigger, but they don't grow exponentially bigger. Okay, so this is one suboptimal alternative. Let's talk about another. And let's go back to our old friend, the minimum mean squared error solution, MMSE. So the idea behind MMSE is we're still going to do an optimization problem, but we're going to do a different optimization problem. We're not going to try to minimize the error probability. We are going to try and minimize, so we're going to try to pick a matrix G such that the expectation of what was actually sent minus what we guess to be sent is minimized. Yeah, so this is going to be the error, and it's going to be a vector. And of course, the error is what we should have minus what we actually have. So this is going to be, in some sense, the truth minus our guess. We'll call that the error vector. And because this is in general a vector, we need to talk about a single dimensional scalar that we need to optimize over. So we're going to take the size of this vector, the norm of the vector. Also, because the vector is technically stochastic, it's got a noise process in there, we're just going to look at the expectation, or the mean, of the square of the error. Mean square error. Oh, minimum mean squared error. Okay, hence the name. All right. So let's get some derivations in here. So again, I'm gonna drop some subscripts, and I might actually end up having to send you this because I do want to get through the rest of the slides today. But let's set it up anyway. So I'm gonna drop the k, so it'll speed things up a bit. So the receipt vector is again r times d times s plus the noise, which means that the mean of the error vector times the conjugate transpose of the received data is going to be the expectation of s minus gr times r conjugate transpose. Again, this is kind of like an outer product. Actually, it is an outer product. You know what? I think it would be better if I'm going to skip to the solution here, and if you're interested in the derivation, I will post my notes rather than me trying to transcribe it here and having everyone try and copy it down. I'm going to ... this and see handout for that explanation. But at the end of the day, we are going to end up with the optimal matrix as the D matrix conjugate transpose times the R matrix conjugate transpose times the R matrix times the D matrix times the D matrix conjugate transpose times the R matrix conjugate transpose plus the noise power times the R matrix, all of that inverted. And it is mildly interesting that as the noise power goes to 0, this thing actually becomes the decorrelator. So that is actually good news, because it means that for any noise power non-zero, then the MMSE will actually dominate the decorrelator in terms of accuracy, or expected accuracy, I should say. Okay, so, and then just to rehash what we just did, you're going to do that for every symbol period k, and then you're going to do these kind of hard decisions after the fact. And implementing this, you will have the minimum average square error over overall symbol periods. Okay. And the benefit of doing it this way is that, again, there's no search to be done. There's a couple of matrices to invert and transpose, but these are algorithmically not complicated. And algorithmically, they grow better as the number of users grows. Okay, so let's talk about how this works or worked in practice, in particular your 3G mobile telephony. It's kind of interesting that there isn't, I've been presenting this as simply you spread your data, you send the spread data, you despread the data, and then job done. But what actually happened in CDMA is 3 separate spreads. So the first was to accomplish orthogonality. And so this was done by what's called a Walsh code. And again, these are all plus minus ones being multiplied in different orders and in different with different correlations. But the idea is that every user in the channel uses a different Walsh code, and that's to ensure that when you're despreading them, everyone is orthogonal, right? So if I multiply Walsh code 2 by Walsh code 1, I'll get 0. And the Walsh code is not super long. So what you can then do is take a long, what's called unoriginally, it's called a long code, and it will mask your transmission. So this is if someone intercepts this transmission and they don't have your long code, then the data is going to be completely scrambled. Okay, so it's implemented for security purposes. And the reason why you want it to be a long code is because you want it to be hard to guess what the code is. And the longer the code is, the longer it would take someone to try to identify its periodicity and derive what the code is. So hence the long code. This would be longer than a symbol period. And then finally, we end up with what's called a short code. And the short code is implemented the same short code for everyone using this base station. So everyone in my cell, if I'm the base station, is going to be using the same short code. And that's so that I can despread it at the base station, but I haven't decoded everything, right? Because everyone has their own unique Walsh code and their unique long code. So even at the base station, if you were to intercept the data here, it would still have the security spreading code in it, and so it would actually be really hard to decode. So these are called, go on now. Wait for it. These are called backhaul channels. And it's how data gets from one base station to another. Okay, so you say that it enters the backhaul network. And those are, sometimes they're microwave, but they are more often than not wireline or fiber optic connections. And so then the idea is that when on the transmission side, if receive user 1 is connected to base station 2, then they're going to despread with base station 2's short code, and then they are going to despread using the security mask number 1, and then they're going to de-orthogonalize with the Walsh code number 1. So what should happen is that these two should match from transmit to receive, and the short code will be unique per base station. Okay, so what can we say? Oh yeah, so how do you construct orthogonal codes? One way to do it is this Walsh-Hadamard operation. And basically you end up nesting square matrices in the corners of bigger square matrices, the result of which would be a 2 to the k size matrix after you do this 2k times. So for example, so W sub 2 would be 1, 1, 1, minus 1, and W sub 4 would be W sub 2, W sub 2, W sub 2, and then the negative. So if you check each of these rows is orthogonal to each of the other rows. Right? If I multiply it and add together, I get 0, unless you're talking about if I multiply and add my own row to my own row, then I get something non-zero. I get 1. Okay, so this is a way to generate orthogonal codes of length L. Right. I like this slide's title. It's very informative, I think. Long code is going to be long for the exact reason that I said before is in 3G, the standard was to implement Pseudonoise that had a period that would repeat itself every 41 days. The idea being that if anyone didn't have access to this code, it would take them a really long time to work out what the code or actually was. And by that time, the data would be long gone or its usefulness would be diminished. So this is a little bit like security by obfuscation, if you like. In that the data is out there, but you can't do anything with it unless you're willing to spend a really long time to search for it. And the other thing is that the long code isn't actually unique to each user, but what is unique is the shift. So if you think of the code itself, lasting 41 days, and it's a whole bunch of pseudo-random numbers, is my long code will start here and run that way. Your long code might start here and run that way. But we're actually all using the same sequence of numbers. We're just, what's random is where our phase shift is within that sequence. That way you don't have to store a whole mess of sequences. You can just store the sequence and the starting index. So it saves space in memory. And then the short code is what's used for encoding in each base station cell. It's generated from this 15-bit maximum length shift register that we talked about a couple days ago. And this, it's actually, you want it to be short because you want either the base station or the mobile to be able to identify where the repetition is. So the idea is that you can tolerate a delay of up to 2 seconds while the mobile phone searches for the quote-unquote start point in the code. So on average, your phone is going to be able to identify the start point faster than 2 seconds, but this is one of the reasons that sometimes it takes a little while to connect to the network, is because your phone might be searching for it's a match for its code to the base station's code, but the base station's code might be up to 2 seconds off from your code. The other kind of neat thing is that the base station will have its own short code per IQ channel. So you can think about, we all talked about a single code, but you can also talk about doing this per in-phase and quadrature channel. It's the same idea. And then everyone is given a unique shift once they've connected. So to this very same sequence, again, we're going to identify user 1 is a shift of 5 bits, or 5 shifts. User 2 would be a shift of 17 bits. And if you are familiar at all with with chipping codes. So I don't know. In 228, I used to ask a question about used gold codes, and this is one implementation where gold codes are used. I'm out of time, but I think that if you're interested, the short code is typically what's called a gold code. Okay, I think that's all I have to say about that. Yeah, I'll open it for questions, but I think we're just about out of time.